With this, let's say we have this theorem that says f of x goes to m, g of x goes to 0, and m can be real or infinity, g of x stays above 0 if there is a neighborhood around created by some real positive sigma around c to which the limit goes, right? And the x goes when prescribing the limit, that then goes to m or 0 respectively for the two functions. We have f of x over g of x going to infinity. And we need to prove for this m of f of x going to either a real number or infinity, and g of x goes to 0 in either case. So let's see. And also let a note, and this is recommended to know anyway, the p of c is sigma. This is a type of notation. I mean, notations vary a lot, but it means it's basically the neighborhood and the interval, open interval, that is centered at the c and going to the left and right by sigma. So c minus sigma up until c plus sigma, excluding the sides and also excluding the c itself. If this is a b in a second, we'll include the middle value c. But in the case of this being denoted by a p, the middle value is excluded because the function doesn't have to be defined at the point for the input, but the limit will still be there. All right, so we have some m. So if m is real, that's the first half of the proof. I can take a real number n, and let's just declare that there will exist some delta 1, delta 2 that will satisfy some certain conditions. And these conditions will sort of be very specific for everything to match together, so it might seem a little bit surprising, but let's see how it clicks. So delta 1 higher than 0 and a real number. So delta 1, there exists delta 1 real number and delta 1 higher than 0, such that for every x in the neighborhood of the c to which the x goes in the limits, but bounded by the d delta 1, we have f of x being in the neighborhood that contains the middle point as well of, let's take this m, and bounded by 1/2 m, which would mean the interval, open interval from 1/2 m into 3/2 m. All right, and the interval to bound it by to the left and right, this 1/2 m, is quite arbitrary choice, but it's also chosen in a way such that the values match in the end, and we get good inequalities and so on. So there exists such a delta, and also there can exist such a delta 2 in reals, delta 2 higher than 0, such that for every x in the neighborhood of c surrounded by the delta 2, we have that the g of x, we can find a delta 2 such that the absolute value of g of x is actually smaller than, and now let's play with a lot of things at the same time, the m that we had from the beginning, smaller than m, there's some real number m, because g of x should go to 0, so it can be arbitrarily small. So we can set it equal, for example, smaller than m, that we denoted right here, and then also let's include the n and make it in a way that will interconnect things in a second for the rest of the proof. And this sounds very random, but it will work out in a second, you'll see. 2 times the absolute value of the n that we define here plus 1. So the absolute value of g of x should be smaller for some delta 2. Exists a delta 2 that for everything in the neighborhood around c by that delta 2, g of x, its absolute value lies lower than this value. Which means if you remove the absolute value, g of x is stuck between strictly unequal between 0 and this value. Another way to express this expression. And now to generalize, make it universally applied to some one symbol instead of delta 1, delta 2, and sigma, I can take sigma, delta 1, and delta 2 in a minimum and set it equal to delta. So the minimum of the 3 will be delta. And then I can have, for every x in the neighborhood of c bounded by this delta, we can have actually something that works for all, but okay, I took the minimum, so we now can talk about what f of x over g of x will be higher than, but also let's first of all, we took the minimum, so it's universal for all 3, and let's just reiterate what this g of x means also. It's useful for this final point. What this means is g of x is between 0 and this. And f of x for anything in the neighborhood of c by delta, by this delta, the minimum of the three Greek letters so far, f of x over g of x will be strictly bigger than anything that's strictly smaller than f of x, and f of x we know is in the neighborhood of 1/2 m. So strictly smaller is already 1/2 m itself because it's not included, it's an open interval. So 1/2 m over and g of x, well, now we need to find something strictly bigger, and the value we have right here is m over 2 times absolute value n plus 1. The m's cancel out, and the 2 and the 1/2 we can flip it, so we get absolute value n plus 1, which is strictly bigger than absolute value n. But n is some arbitrary real number, and so that f of x over g of x, as we want from this theorem, goes to infinity. So that's the point, okay? We made f of x over g of x strictly bigger than some real value n. And now again, we'll do the same thing for infinity. We'll be far faster, alright? So if m is infinity, we have this. We can again take a real n, and there will exist some delta 1, such that for every x, in the neighborhood bounded by this delta 1, we have the following. We don't have actually the same thing like before, but this time we will say f of x is higher than 1. And this is logical. M goes to infinity, so higher than 1. Okay, why not choose it? I mean, it sounds like a small number, but why not? So now we can say, of course, for f of x, we can find a delta that f of x will be forever higher than 1, because f of x is a limit going to infinity. Because now we said the case when m is infinity. Before we were taking care of the case as m is real. And also we can find delta 2 such that for everything in its neighborhood, g of x its absolute value, and this time we can make it simpler. We're not dealing with an m here or a complicatedly, or not so complicated, but not so trivially defined interval that f of x falls into. Now it's simpler, it's just 1. G of x will also make simpler. We won't have to include in the numerator an m re-mentioned again, but I'll just do 1 over absolute value n plus 1. We took an n again. Okay, and now what do we do? We can again take a minimum of all three so far. So the sigma, delta 1, delta 2, and we can have that equal to delta. So we set that equal to delta, and then for every delta, for every x in the neighborhood defined by delta in the inputs, the neighborhood x not containing the c itself but containing the neighborhood around it, we have that f of x over g of x is now strictly bigger than what? We'll do a similar idea. Well, strictly bigger than 1 in the case of f, so that works, and g of x we just need something slightly bigger than g. And again we have something like that, so we have this, we can put that in the denominator. This is true. You can just check these inequalities, and from them directly we yield this, the f of x over g of x, what is strictly bigger than. You just try to look through it. Or you could choose, as you see, different numbers as well, but the ones are for simplicity, sort of. So that's the point there. So basically we have this, which is strictly bigger than some real value n. And again, that means f of x over g of x will go to infinity because n was some whatever real number, and anyhow large real number. So these were the two parts of the proof.